Good afternoon, everyone. Hi there. Thank you for coming. My name is Greg Kameka. I'm a 77 graduate of Weinberg College of Arts and Sciences, an 85 graduate of Kellogg, member of the Day at NU Executive Board, and we thank you for joining us today. First, a little, because I got it, there we go. Sorry about that. I will skip most of the detail, but thank you for joining us today. First off, a little bit of housekeeping. As you might have heard earlier today, you will be getting a survey in the mail at the conclusion of this event. We do ask you to please take some time to complete that. We do value your comments. We read every comment that's in there. They have certainly been useful to us over past years in making improvements and enhancements to the program. Right? So now I'd like to introduce our featured speaker. You know, I might start off by saying I first met Joe about 40 years ago. He was the master at the College of Community Studies when I was a sophomore, junior, and senior, building up North Campus. So Joe is a professor of civil and environmental engineering, an associate dean for faculty affairs at McCormick School of Engineering. He's got both his PhD and master's from McCormick. Today, Professor Schofer will discuss one of the most impressive engineering feats in modern history, the construction of the Panama Canal. More than a century after its completion, the canal is still a key component of global trade, and a massive project to expand the canal's capacity is nearing completion. This afternoon, Joe will use historic and modern photos to describe the engineering and managerial breakthroughs that made the canal's construction possible. He'll also explain the canal's current expansion program, the workings of its innovative new locks, and the role it will continue to play in the 21st century global logistics. Joe's presentation is titled, "The Panama Canal, How Did They Build It, and What is Its Future?" Right? And also you will see that on all your seats today, Joe leads a tour with the Northwestern Alumni Travel every year, taking you through the Panama Canal, and there's some information for next year's trip if you want to follow that more. Anyway, please join me in welcoming Professor Joe Schofer.
So, can you hear me? Can you hear me now? No. Okay. I don't know what to do about that. Are we on? Are we on? Is that working?
Try that.
Okay, better? I'll do my best. If you can't hear me, here's the ground rule. First of all, I like to walk around because I found that after 40 years of teaching, it's much harder to hit a moving target, and it also keeps people awake. So if you can't hear me, then why don't you come up to, there's a couple seats right here. It might help, and you might be able to see better as well. So I'm going to move around. If you cannot hear me and you want to hear me, raise your hand. Okay? So I'm a civil engineer. Right? My wife is not with me today. My wife would tell you he's a civil engineer after about 10 o'clock in the morning. I want to share with you something of the history of the Panama Canal. How many of you have read David McCulloch's book, The Path Between the Seas? Okay, so if any questions, I'll refer them to you. Okay, I am not going to do a political history. Oh, so another engineer. Thank you very much. I'm not going to do a political history. I'm going to talk about engineering. And for those of you that have never had an engineering lecture, this will be a great experience for you, and I think most of you will survive. So I have some pictures, and I won't tell you everything about every detail of the picture, but this is one of my favorite pictures, which I discovered in a library in Kansas. The archives of the Panama Canal are everywhere because the people that worked on the canal came from everywhere and went back to those places and ended up putting things in their library. And this is a picture of the French work on the Panama Canal in 1888. Now, I know that you remember this, but the Panama Canal was constructed by the Americans between 1904 and 1914. So this was way before the Americans got there. And it's a very old picture and a little bit hard to see the way I presented it. But one of the messages here is the French approach was extraordinarily labor intensive with very modest technology, which is one of the things that got them into trouble. Just to remind you a bit, I'm sorry about that, I'll try to stay in one place. Just to remind you a bit about the history. The French made an effort to build the canal in the late part of the 19th century. The effort was led by Ferdinand de Lesseps. You remember him very well because he organized the construction of the Suez Canal. He was not an engineer, he was not a technical person, he was an investor, a financier, an organizer. And he did a rather good job with the Suez Canal, though circumstances were substantially different. The U.S. got involved not for financial reasons, which is why de Lesseps was trying to build a canal in Panama. He felt omnipotent, he felt he could build a canal anywhere. The U.S. got involved for strategic reasons, and really can trace it back to the Spanish-American War, the explosion that destroyed the U.S. Battleship Maine in Havana Harbor, which, as best I understand from history, later turned out to be an accident rather than an act of war. Teddy Roosevelt was Secretary of the Navy, later to become president. The U.S. battleship Oregon was dispatched from San Francisco, where it was at the time, to head for Havana. That trip took 67 days. There were 5 coal stops to refuel, and it was one incident, but it was an incident that helped drive the motivation to build this canal, to connect the two oceans, and to put the United States in a situation where it could be a global maritime power and have a navy in literally both parts of the world, and that can move between the two. The challenges of building this canal were substantial. And it's fascinating to compare what the builders of the canal went through then to what we might encounter now, and what we really are encountering now because of the expansion program. The site of the construction was 2,000 miles from home being the continental United States. The conditions were extraordinarily primitive. There was a terrible risk of disease, yellow fever and malaria. There was really a complete lack of understanding of what transmitted and what caused those diseases. The French had failed in their effort in the years shown there, 1881 to 1904. The United States, through, I could say, hook and by crook, but I'm not doing a political history, got involved in building the canal and was able to complete it in 10 years. By the way, I should go back and just point out that that's a steam shovel that's buried in a rock slide, which is something that was very common during the construction of the canal. So what I want to tell you about is how this mega project, this really large project, was engineered. The steps that the leadership and the managers went through to get it right. And the keys were creativity, finding a creative solution, understanding a problem and finding a creative solution, picking the right technology, and having an organization that really worked. And so I break that down into these 4 categories, and I'm going to talk about these 4 elements. Creating the right environment. Remember I said it was 2,000 miles from home and disease was endemic and the living conditions were terrible. It was not a situation where it was easy at all to get people to go to work there. So they solved that problem. They came up with the right design, and it's not something that people talk about very much, but the fact that they chose a lock canal rather than a sea level canal really made all the difference. It cut the construction time in half, it cut the costs in half, and they ended up with something that worked very well. They used the right tools, and I'll show you some of the tools that they used, and they organized themselves in a way to understand what the fundamental problem was, and we'll get to that in a moment. So I keep getting ahead of myself. But that's a classic picture. Everybody shows that picture. I'm sure you've seen it before. Teddy Roosevelt is in the white suit, sitting in the driver's seat of the steam shovel. He was the first president of the United States to leave the continental United States while he was president. This was his project. He needed to go there. He needed to be on the scene. You can see presidents continue to do that, right? They just follow where the photographers are. So the 4 points I wanted to cover: the right environment. Disease was endemic, and I told you about that. The picture is a picture of William Gorgas, who was the physician in charge, and he worked under 3 chief engineers, and there were 3 chief engineers, and I'll tell you about them. John Wallace, John Stevens, and Goethals, William Goethals, who, in that order. And the quote I picked out, and I've read a lot of the history that David McCulloch read to write his book. And this is a quote from Stevens, who was the middle chief engineer and really was probably the most important of the chief engineers. And the bold is what's critical. He says, disease and death would have conquered de Lesseps, even if his finances held out, which they didn't. And they would have conquered us if General Gorgas and his staff had not so successfully handled the situation. And what's fascinating to me is that I've looked at the history, and that label there that says 58 years of disbelief is a reminder that you can go back in the medical literature at least 58 years and find people who were saying, you know, this disease is connected to mosquitoes. Something that causes this disease is carried by mosquitoes. And there was yes, sir.
I beg your pardon for interrupting, but could you turn down the gain on your microphone?
Could I turn down the gain on my microphone? That's a really good. I would love to do that.
I think you're getting close to that. This part of it.
Can you hear me now?
Yes.
Okay. Not at all.
Can you move your mic up your lapel?
I don't think I think the union rules say I'm not allowed to do this. How about that? That doesn't do anything. Some say yes, some say no. Okay. So while they're playing, while they're working with this, I'll walk into the, yes, that's exactly. Right, you need somebody's grandchildren. There were all kinds of theories about what caused malaria and yellow fever. These diseases were carried by two different mosquitoes. And during the reign of the first chief engineer, who was John Wallace, they made an effort to get the resources from the government in Washington to address the mosquitoes, and there was such skepticism that mosquitoes had anything to do with the disease that they couldn't get the resources. When Stevens came in as the second chief engineer after a year, Wallace only lasted a year, he basically stopped all work and said, we're going to clean up this place, and then we'll go back to work. And so they focused on eradicating mosquitoes. And so here you see one example of that. So those of you that know something about mosquitoes know they breed in water, and the thing you want to do is suffocate the larvae when they're trying to breed. So you coat the water with oil and you're in business. They literally wiped out the mosquitoes in the construction zone in less than a year. And it was tremendously effective and tremendously inexpensive. And I'm not going to waste time showing the statistics, but if you look at the death rate on an annual basis, it just dropped almost to zero. Well, it didn't drop to zero because people were still killed in construction accidents and for other reasons. But that really opened the door. That made it possible to solve this problem of building this canal. The other thing they did was they built infrastructure so that people have places to live. They built very high quality infrastructure. So the picture in the upper right is quarters for married couples. So most of the employees, most of the engineers, most of the workers were men, but they encouraged the men to be married because they felt that they would be more stable and more reliable. Apparently there's some evidence that continues along those lines. The picture in the lower right is I'm sure it's a staged picture. They got everybody to dress up and for the photograph. But that's the reading room of the Isthmian Canal Commission. This became the best place in the world for an engineer to work in the period 1905 to 1914. The salaries were highest. It was most interesting, and the career opportunities ahead were fantastic. So by addressing this issue of building the infrastructure and changing the environment, the Panama Canal construction site became a playground for the wealthy in the United States. So people went there for vacations. There were tours there. So Greg mentioned that you could come with us for a vacation next February, and the mosquitoes will probably not be quite the same problem. The second point, and probably the most important key to solving this problem, was coming up with the right design. So for those of you that are not map-oriented, this is an old map of the Panama Canal. And it's oriented in a funny way because north is in that direction. The Panama Canal basically runs northwest to southeast, very close to a north-south alignment. On the left is the Caribbean Sea, really connected to the Atlantic Ocean. We call that the Atlantic side. On the right, the Pacific side. This is the continental divide. This is the highest point on the continent. The continent's very narrow. It's about 50 miles wide. The highest point is right through there. And the trick was, how are we going to get through there? Are we going to get ships, literally ships through the mountains? And de Lesseps, who was first to the gate here and to try to build this canal, was pushed very hard for a sea level canal because that's what he knew from Suez. And if I'm not going to, I don't bring the picture of Suez, but Suez is a desert. It's flat. There's no mountains there. It's with all due respect to de Lesseps, it's a much easier job. And whether to build a lock canal or a sea level canal was something that was debated between 1879 and really not settled till 1906. So remember, the United States got there in 1904. So we were there 2 years before this critical design feature was settled, and it was settled in a wonderfully interesting mixture of politics and technology and engineering. There was a great fear of locks because people didn't know how locks worked. It turned out that the busiest locks in the world at that point in time were the Sioux locks between Lake Superior and connected to Lake Michigan. And when finally they brought in the chief engineer of the Sioux locks to sit on the Isthmian Canal Commission, he helped tip the vote to say, I know how to do this, locks work really well, and it's nothing to be concerned about. In effect, we got advice from people around the world who had some knowledge of marine systems and locks and ship operations. And the preponderance of votes that came from the European representatives were for a sea level canal. And it was the Americans who outweighed them on the Isthmian Canal Commission who provided the final piece of advice that said, look, we can do this, it's going to save us money, it's going to save us time, and we can make these locks work. The politics are quite interesting because in the end this was a decision that was made by the Congress. It was a point in time when the Congress apparently had the ability to make decisions. And the Congress directed the president to do this. And Stevens, who had just become, really months before the congressional debate, the chief engineer, at first was agnostic on the issue, then read all the technical studies. And the technical studies, it turns out, are extraordinarily accessible in the literature. Well, they're on the web, and my students will tell you everything is on the web. You can easily find that. And what really swung the vote was that there was a minority report to this International Board of Consulting Engineers that said a lock canal is going to be more efficient for the following reasons. Stevens picked that up. He was literally convinced of that in a very short period of time and testified before Congress. Congress supported the vote, and it went to the president, and the decision was made to lock in the idea of a lock canal at the end of June in 1906. This is not a trivial decision. This is a critical decision. So now you got to put on your technical hat a little bit. This is a cross-section of that isthmus, that part of Panama. It's about 50 miles wide. And you see two models. So this is the Pacific side, the south, the Atlantic side, and the north. The continental divide is here. Those are those mountains that you saw on that map. If the decision was made to build a sea level canal, the amount of excavation necessary is indicated by the yellow shading up here. A decision to build a lock canal left the amount of excavation as indicated by the red shading here. There's a huge difference. Now, I hope you like this because I shaded this myself, and it took me a really long time to do this. And what did they do? They did something that looks so simple, especially looks simple if you go there. And that is, there's a large river that flows through Panama called the Chagres River. It flows from the mountains of Panama out to the Atlantic. And what they did was they built a dam here. And so they metered the flow of that river. So when you build a dam, what do you normally find behind the dam? A lake. So this created this fantastic lake, which is called Gatun Lake. And by creating that lake, what they did was they created 23 and a half miles of channel that they didn't have to dig by building that dam. Now, it turns out, if you go there, when you go there and you look at the dam is very unimpressive. it looks like a golf course because it's an earth-filled dam. So it's all green and mowed and pretty, and yet that was the trick that made it possible to build a canal with relatively small amount of excavation. Relatively, it wasn't a small amount. If I remember correctly, the amount of earth moved to build the Panama Canal was about the size of an American football field, 23 miles high. So that's a lot, but it would have been 4 times that if they had gone for the lock canal. Or for the sea level canal. And what you see here in the dark shading is those are the locks. So what you're doing is you're lifting the ship up. You're saying, okay, I created this lake. It's 85 feet above sea level, built this dam, at the time the largest earth-filled dam in the world. And all I have to do is lift those ships up. And people have been lifting ships up with locks for 1,000 years. So this was not such a big deal once that decision was made. The third key to solving this problem was having the right equipment. And somebody said, and I think McCulloch probably quoted this in his book, that the technology that the French used, I can't do that, was like trying to dig it with a teaspoon. And so here in the top 2 pictures are some of the French technologies. And the thing to look at is everything is small. The little rail cars are small, and there are a lot of people. And the United States really went the other way. Big stuff, a lot of people, but many, many fewer people, and operating at very high rates of speed. So you can see that digging through this cut, you have power shovels there, steam shovels, much more capacious than what the French were using. And the railroad cars, they built special railroad cars so they were flat, open on one side, and they had that flat wall on the other side. So they could load it from that open side, and literally the trains didn't stop moving. They just moved very slowly, loaded them very quickly, took them out, dumped them. The fact that they were only one-sided meant that they could move a device across the cars from car to car and just empty the train in a matter of minutes. Okay, so you can see one of the shovels there. Here's the shovel up close. One of the things that fascinates me about the Panama Canal is you can trace, I shouldn't say it that way, I can trace the equipment that was used in the Panama Canal to the Midwest, to Milwaukee, to Detroit, to Bay City, Michigan, to, were you here when we reversed the direction of the Chicago River? Probably not. So that was, if I remember correctly, January 1st, 1900 was when they blew the final dam and reversed the river. The equipment that was used there, if you look at the pictures, you see the same equipment used in Panama. So that one project learned from another, and the scale was very, very large. So it's interesting if you look at the technology that they used. Yes?
Was the railroad already there, or did they build that?
Well, that's a good question. And I don't have time to answer that question, but if I did, what I would say is, yes, the railroad was there, because the railroad was built in 1849 for the gold rush, because that was the fastest way to get to California. You take a boat down to Panama, you get on the train, in a day you'd ride across and you'd take a boat back up. It was the most expensive train ride in the world at that point in time. It was $25 for 50 miles. That railroad was completely rebuilt by the Americans because it was very small scale and inadequate. But if you go there now, that railroad exists and it's running right now. And the fascinating part to me is that the operator of that railroad is a company called the Kansas City Southern Railroad. So, okay. So it's very, very important. But your question reminds me that all the technology that they used was rail-based, because diesel engines and rubber-tired vehicles, which are tremendously more flexible, didn't exist then, okay? So everything was rail-based, and when they had to move this large shovel along, they had to reposition the rail. They had to move the rail. So that's why it says 6 move-up men. So they were the guys that reorganized the track so they could move this. This is much, much larger than anything that the French were using. I love this picture. It's Panama, you know, it's really hot there, and the formally dressed people, all the engineers and management all wore white suits. Now, my experience is if I wear a white suit from my bedroom down to the kitchen, I get a spot on it. But they seem to be able to do this. This is Calabre Cut, or Gaillard Cut, which is the Continental Divide, the deepest amount of excavation. I have a different picture of this where you can see they're operating on 7 different levels at the same time. It's a very active construction site, and you could see it. You shouldn't be surprised that in a setting like this, they had huge problems with slides, that is, material sliding back in. The fourth point I wanted to get to is that they used a right method. And what's a right method? The first 2 chief engineers that they hired, John Wallace and John Stevens, I cribbed those articles from the New York Times, contemporary articles in 1904, 1905, announcing their appointments. They were both railroad people. And why were they railroad people? Because what was going on was that somebody figured out that the real problem was not digging the material out. It was moving it to someplace else so that you have a place for the canal. So the big part of this problem was transportation. So that dam that I told you about that was really critical to building a lock canal, well, that dam took material. And where did the material come from? It came from the Gaillard Cut and other places where they were digging, and they had to move it 20, 30 miles to this other location. So the transportation part was absolutely critical. The railroad was the backbone. It was the lifeline. So in response to your question, I did have it here, that the railroad was there, but they completely rebuilt it because the scale and the capacity of the railroad that had been built earlier and that the French had added to was completely inadequate. These guys also were Chicago guys, which is fascinating to me. Wallace was chief engineer of a railroad called the Illinois Central, which became the Illinois Central Gulf, which now is part of the Canadian National. But remember the song, The City of New Orleans? You don't remember that? Okay. Well, I'll sing it to you later, but that's their train. And that's the Illinois Central. So he came from there. He got very frustrated. And by the way, that was his salary, and it was a monstrous salary at that point in time. And a year later, they hired Wallace, and they gave another $5,000 a year, and apparently that worked. Wallace got frustrated with the bureaucracy and didn't last. Stevens was the guy that solved the problem. He was the one that saw the idea that, first of all, it's got to be a lock canal to make this work, and that the railroad was critical to the success. So the strategy that Stevens used was to organize the construction so they'd pull empty trains up the hill, load them, and pull the loaded trains down the hill. So it meant that they needed less motive power to do that. The scale of the railroad operation was huge. Trains every 3 minutes moving through the canal zone to move spoils to both to the dam and to breakwaters at both ends. This is a picture that fascinates me. This is a rail shop that they needed to repair facilities. Goethals, who's the third chief engineer and the final chief engineer, and he was the one that really finished the construction. He was a military guy. Roosevelt said, I need to hire the third engineer who can't quit. Wallace quit. Stevens quit. The theory is that Stevens got bored with it. It was like he could see the end and he thought, I think I'll do something else. So he went to Russia and built railroads in Russia. And really had a terrific career and was, if you read some of his stuff, he really had a clear sense of the role and the significance of engineers and engineering in society. Goethals traveled around the work site in this steam-powered car. Again, the rubber tires and internal combustion engines were rare, so this is very common. This is an odd picture because it looks dark, but he had the car painted yellow, and the workers called it the yellow peril because they would see him coming and everybody would start working harder and faster. So here are those three chief engineers, Wallace, Stevens, and Goethals, George Goethals, got his name wrong. He battled the bureaucracy and wasn't successful. There was a point in time when Wallace sent a telegram to Washington asking for some resources, and he got a message back that said, use the mail, telegrams are too expensive. Stevens was the creative guy. He was, I called him in a baseball terminology, he was the middle reliever. He was the one that really figured out how to solve this problem. He developed the key designs. He was the one that said, let's solve the living environment problem first, and then we'll build the canal. And when he quit and went back to the railroad industry, Goethals came in. He was from the Army Corps of Engineers, and he was an efficiency expert. He was the metrics guy. He measured performance. So the performance of every unit on the job was measured on a daily basis, and it was published in the newspaper. The newspaper's called the Canal Record. You can go online and find copies of the newspaper. And he created a competition that everybody wanted to be the fastest and dig the most in a given day. So he was very good about kind of building up this capacity to deliver a product efficiency. So what are the lessons? Well, to me, there are a lot of lessons, and I find these lessons, when I talk to junior engineers, undergraduate engineers, there's nothing that I've learned from this that isn't applicable exactly right now. The starting point is figure out what the problem is. Let's try to understand what the problem is, and from that point on, getting a solution is going to be a lot easier. So, Bob, you know about this, because this is really what we do in our freshman engineering course, design thinking and communication. We try to get kids to think about what is really the problem as opposed to what is the solution you had in your back pocket that you want to deploy. And that's really what killed de Lesseps, that he had the solution before he saw Panama, before he understood the problem. It was really evidence-driven decision making. They realized how important it was to resolve the issue of the environment, to work at a scale that's appropriate to the problem. And in the end, Goethals came in and said, let's deliver a product. Let's stay on time, let's stay on budget, and let's keep this thing moving. I put this picture in here because this, as an engineer, this fascinates me. When they were designing the spillway for the Gatun Dam, and I haven't shown you that, but when you come with us, you'll see it. They built scale models of that spillway and tested them, and that's what you see there. They built three different designs, or two or three different designs, and tested them. So you didn't have the computational ability that we have now to test these things. So they built scale models, and there they are in their white engineers' business suits in the heat of the day in Panama looking at that. For those of you that are thinking about the question and didn't ask it, the rough estimate of the cost at the time of building was $375 million, which somebody in the government spent $375 million since I started talking. And if you bring that up to a current estimate, it's about $9 billion, which really was not very much. Okay, so that's the history. So let me tell you a little bit about the canal today. And the starting point, because this is a question I get a lot, is how does it work? Well, most locks work the same way. There are no pumps. It's all driven by gravity. And what happens is that water starts at the top, and the top is Gatun Lake. Remember, they built that dam, and they created that lake. And when a ship transits through the canal, moves through the locks, the water moves down with the ship. Okay, well, how does it go up? Well, exactly the same way. It's down here, and then water from the top comes here and floats the ship up. So one direction or another, it doesn't make a difference. So for those of you that are geometrically structured in your thinking, what you're really doing when you move a ship through the canal is you're taking a rectangular cube of water that happens to have a ship in it, and it's the size of the lock. And I know you know this, but the current Panama Canal lock is 1,000 feet long, 110 feet wide, and about 50 or 60 feet deep. But you don't move all the water, you just move the ship down one notch, which is about 29 feet. So you could do the math. 1,000 feet long, 110 feet wide, 29 feet high, that's a cube of water that just drops down by gravity, and the ship goes with it, okay? And you've probably figured this out already, but that's 52 million gallons worth of water. And so when you're transiting ships through the Panama Canal, if you'll allow me to use the analogy, it's like flushing a 52 million gallon toilet, right? That water moves out. But it's fresh water, Panama is a rainforest, so that lake gets filled with fresh water, and it moves down to the ocean. So every transit of the canal, every ship going through is taking with it 52 million gallons worth of fresh water. So one of the things to think about is, well, you better have enough fresh water to make this go, or it isn't going to go. And they're right now building bigger locks, and bigger locks are going to ask for more water. Okay, so this is a picture of a container ship going through probably, what is that, Pedro Miguel locks on the Pacific side. And you can't read this, and why do I put this up there? Because I'm an engineer and I like to think about numbers. What's really important? They move about 12,500 ships through the canal every year, both directions. Actually, they move more than that. They just don't count the tuna fishing boats that are going short distances. These are ships involved in global commerce. The millionth ship went through in October 2010. By the way, 12,000 plus ships a year means about 34, 35 ships a day, both directions. So it doesn't sound huge, but when you go there, it's full of ships, okay, because the space is not that large. What's the market? The main market is East Coast United States to Asia. About 40% of the tons are southbound. Southbound means they're going to Asia, and 29% are northbound, and where are the rest? The rest is South American, so it's not going far. So that 40% that's going to Asia, so you think about, well, all the imports are coming here and we're not exporting anything. What we're exporting is mostly bulk commodities. And so, which is why the Panama Canal is critically important to the Midwest, because it's corn, it's grain, it's soybeans that are going down the Mississippi River, going by rail to the Gulf Coast, and going out through the Panama Canal. Average time to transit the canal is 12 hours. So it's a day trip. Except if you got a reservation, which you can get if you're willing to spend a little more money, you can cut a couple of hours off that because you go to the head of the line. Average canal waters time, that is when you're in the vicinity and you can say, I see it over there, but I'm not going through, is about 32 hours unless you have a reservation. Total tolls the year before were $2 billion, aggregate tolls. So somebody asked me a long time ago, does it cost money to go through? Oh, yes, it costs a lot of money to go through the Panama Canal. The average toll is $160,000, which sounds like a lot of money, except if you're running a container ship and it's costing you, let's see, what does it cost you to operate a container ship a day? By the container ships, the ships are really, there's an oversupply and they're cheap today. $10,000 a day. So if you went around, you would add another 10 to 15 days on there. So these tolls are set by smart people working for the Panama Canal Authority who say, let me try to think, how much am I saving you? How much of that can I take back to run this canal? It's by the way, United Airlines prices the same way, right? Okay. So average toll, $160,000. So these are only pictures, but they're contemporary pictures. They're my pictures that show you what it looks like today. So Gatun Locks in the upper left. This is that Continental Divide. This is the area of deepest cut. Gold Hill on the left and Contractor Hill on the right. That bridge is called Centennial Bridge. A Bridge of the Americas, if you're thinking about that, that's a little bit further, about 7 or 8 miles further south. There are right now only 2 permanent connections across the canal. Bridge of the Americas, which is near Panama City, and Centennial Bridge, which is here, and there's another one that's under construction right now. Ship going through one of the locks, and the little locomotives, you can see them. So just to dispel a myth, the locomotives do not pull the ships, they just position them in the lock. Okay, so, and then somebody says, well, but they used to. And no, the locomotives never pull the ships. The ships always go through on their own power. And the locomotives simply position them, which is really interesting the way that happens. I'm going to tell you more than you want to hear about the pricing structure because I'm really deeply curious about that. Because that's what makes it go on the financial side. Water makes it go on the physical side. The tolls are based on what kind of ship. What are you carrying? What's the value of what you're carrying? The more valuable it is, the more they can charge. And what's the scale of the ship? And so the scale is really, fundamentally, it's measured in terms of volume usually people talk about ships in terms of weight and different kind of weight measure, but volume is where the value is. So they have an interesting scheme for calculating volume, which is called Panama Canal Universal Measurement System, or PCUMS. It's 100 cubic feet. What happens is that when you build your next container ship, it's certified for a particular volume by the shipbuilder, and that gets put in an international record. And so the Panama Canal Commission can look and say, okay, I know what the volume of your ship is, and so I can price it at that level. And there's some differences. So if you're in a big cruise ship, the price is right now, it just went up beginning of April, $138 a berth. Okay, so if you have 5,000 passengers, multiply it out, 130, and they don't go feeling the beds, are they warm? They just say, what's the capacity, and do you have any passengers on board? If you have 2 passengers on board, you pay $138 times the capacity of the ship. So they're very direct on that. By the way, you have to pay it electronically in advance. They don't take credit. Okay, the pricing gets moderately complicated. I've included this picture, so here's a couple of these locomotives lined up. They always bring the lines out to the ships in a rowboat. When you ask people with the Panama Canal Authority, have you ever seen an outboard motor? You know, and the answer is a rowboat never fails to start. Okay, so they always do this. Those are tolls. That's for tolls. Then there's a whole bunch of services that are extra on top of tolls. So pilotage, you have to have a pilot on board. So you went through in a submarine, didn't you? Yeah, but you had a pilot from the Panama Canal Authority. It has to be that way. For the wires for the locomotives, they're $300 a wire. Panama Canal Authority decides how many you need. And onboard line handling. So my experience has been, even in a tiny ship, they'll take on board workers from the Panama Canal Authority to handle the lines because they know how to do it. And the people on your ship may not know how to do it because they're not doing it day by day. A bunch of other fees. There's a fee, a $30,000 fee for daytime passage. And so, Amy, you know about this. I've gone through at night. You don't see a lot at night. So it would be kind of like touring the Northwestern campus at night with the lights off. And so that seems like a lot, but they've figured out that if you're on a container ship going through at night, it's not an issue, right? But if you're on a cruise ship, that's why you went, right? So going through in the daytime it really makes a difference. It's a huge difference. Here's some examples of average tolls paid by different ships. So this is a big passenger ship, and that average is about $190,000 spread over a lot of people. I mean, if you go around with your little straw basket and say, I need $14 for everybody, it's okay. I think the last small ship, the 200 passenger ship that we've used, pays about $50,000 in tolls, and $30,000 of that is for the daytime passage. So you can see that. When you think about it, what's really going on is the pricing is proportional to the size and the value of what you got in there. And that's why the container ship pays a lot. And the auto carrier pays a lot. So cars that are, for example, built in Japan, they're coming here in ships like that. Ro-ro means roll on, roll off. So cars get driven on and driven off. And it's completely sealed because you don't want the high-value motor vehicles exposed to the sea air. Just a quick idea about where the money goes. The orange bars are the amount of money that gets swept to the budget of Panama, of the nation of Panama from the canal. It's about $1 billion a year. So I remember I told you the average toll was, the aggregate toll last year was $2 billion. Well, they make a lot more money. That's the toll. Then there are the fees for all these services. And then they have that dam there. Remember that dam? They generate electricity with that dam, and they sell that electricity, and they purify potable water, and they sell that. So there's a lot of other sources of revenue. So $1 billion a year is significant for Panama. A quick word about containers, because I showed you container ships. This is a big market for the Panama Canal. The fact that we can move goods in containers made it possible for manufacturing in the United States to move to Asia, because otherwise it would have been completely impossible. Why is that? Because containers are standard. There's a few standard sizes. They're sealed steel boxes, so you don't have a problem with containers that we used to call shrinkage, which is there's less stuff comes out at the other end than you put in at the beginning. And handling them is really, really efficient because they can go on ships and trains and trucks. And the standard size that we talk about is a TEU, 20-foot equivalent unit, which is 20 by 8 by 8.5. It weighs about, typically what you do is you work with doubles, so that's 40 feet long instead of 20, and they weigh about 70,000 pounds. So you can get a lot of rubber duckies or other things in there, very capacious. And the expansion program that the canal is going through is really driven by the numbers here. So this red line, this is a timeline. It ends in 2011. This is the latest data I could get. This is the number of transits per year. It's around, where it was 12.5, 13, 14,000. And it's fairly flat. And the yellow line is the total volume of cargo moving through, which is growing. So, it's growing fast, and it's measured in this odd unit called Panama Canal Uniform Measurement System, or 100 cubic feet. So what's the explanation? If the number of ships is fairly constant, but the amount of cargo is more, what's happening with the ships? The ships are getting a lot bigger. And the reason ships are getting bigger is that you can run a ship that's very large with a crew of 10 people. A lot of things are automated. You don't need a lot of people there. And so there are huge scale economy advantages in working with big ships. So this is one of my favorite ships. It's the NYK Diana. Anybody ever sailed on Crystal Cruise Lines? Okay. So Crystal is a Japanese company. Used to be. It was just sold. And their big business was actually in the cargo business. So this is one of their ships. I was taking this from another Crystal ship, which didn't look like this. This is a big ship. And this is the biggest, this is a Panamax ship. It's the biggest ship that can get through the canal. It's 105 feet wide. Remember I told you how wide were the locks? 110. So no problem, right? You got 5 feet, you got 30 inches on a side, and you got these locomotives that are keeping the ship in line. So they don't touch. They really don't touch the side. It is amazing. But when bigger ships get bigger, you're stuck. You really can't get them through. So that's one driver for the expansion program. Another is competition. There's a huge amount of competition. So this is a map of the U.S. railroad network. So what's happening here is that a lot of this container freight is coming into West Coast ports. Let's see if I can make that work. No, I can't. Coming into mostly Port of LA and Long Beach, which is the busiest, but also a little bit in San Francisco and some in Seattle. And it's coming by rail. And rail is more expensive, but it's faster. So it depends on what you've got in there. And the pricing goes back and forth. The Panama Canal Authority is desperately trying to compete with the rail. And they have to do something. And one of the ways to do that is to open up the capacity for larger ships. There's also rail connections out of Mexico. There's a port in Mexico that's really run by Maersk, which is the big shipping line. And that red railroad that comes up in the United States, that's the Kansas City Southern again. It's another U.S. Connection. There's that competition. The Suez Canal really isn't much competition for the Panama Canal. People write about it, but there's not much evidence of that. You've heard about the Nicaraguan Canal proposal. I don't know if it's real or not, but it seems to be a significant threat. There's also a proposal for an overland connection in Colombia. I'll show you that in a map in a sec. And there's been a few ships that have made it through the Northwest Passage over the Arctic, and global warming is contributing to that. It doesn't look like that's going to come really quickly, but something to be concerned about. Here's a couple words about the Nicaraguan Canal. So the Panama Canal is down here. Nicaragua is up further north. Nicaragua was in play when the idea for the Panama Canal first came about. So this is not at all a new idea. It is a very hard canal to build. On the one hand, you have Lake Nicaragua in the middle, which saves a lot of construction. On the other hand, you've got a distance of 173 miles, some 60 miles in rough terrain. It would be 25 times the amount of excavation done for the Panama Canal. And the claim is a Chinese investor. The claim is he's going to do it in 5 years, which is, I don't think that's likely to happen. And the response of the Panama Canal Authority is, okay, if you guys do that, we'll build bigger locks. We know how to do that already. So they're concerned, but I don't think that they feel it's a huge threat. So what's the expansion program? It's bigger ships, more competition, lead not to a new canal, but to new locks, because the locks are the bottleneck. Remember, 110 feet wide. So they're building new locks. They're done. They're a few months away from completion of the project. And they're 1,400 feet long. The old locks are 1,000. What's really important is they're 180 feet wide. So right now, the Panama Canal Authority is allowing ships up to 160 feet wide into the canal. So wider and deeper. So it means bigger ships, more capacious ships. They're one design locks, which saved a huge amount of money. It is designed for the set on the north, and the set on the south is exactly the same. It wasn't customized. They're also deepening the channel, so that's what you see here. There's a dredge at work. They're raising the level of the lake by a foot and a half, 18 inches. That allows them to store more water. You need more water because you have bigger locks, okay? And water is a critical issue. It's a rainforest. There's been a drought there the last couple of years. Panama Canal Authority has twice issued a notice to mariners that says, we are going to restrict the draft of the ships that you bring in by 6 inches, which doesn't sound like much. 6 inches is a 15% reduction in the capacity of the ship. So it's significant. So they are worried about that. And they're widening this cut, and that's what you see here. It's a little, you can't tell this, but these are not the kind of construction vehicles that you see on the Northwestern campus. They're the kind of vehicles you see in a giant open pit copper mine. They're 100-ton capacity vehicles. So here's got to go through this quickly. Map we saw before. The new locks at the south end are here, at the north end are there. The channel gets a little bit deeper, and that lake gets deeper by raising the top of the dam just a little bit. So here's a picture of Cocoli locks. This is the new locks on the south side. It's a little bit hard to tell, but the old locks are over there. Up at the top, that's Miraflores lock, which is close to the Pacific end. There's a little lake, and then there's Pedro Miguel up further north. This new set of locks bypasses both of them. So there's a 5-mile channel that they created for this, and the new locks are right in here. You cannot tell that they're larger, but they are much larger. They're also have given up the idea of miter gates that open and close like this, and they've gone over to rolling gates, which those of you that have older homes will know them as pocket doors. Yes. And they're doubled, and the reason they're doubled is so I can pull one in and work on it, and keep the lock going. They're also about 4,000 tons a piece. And what you see over here is a set of, under construction, water-saving basins. So what they're going to do is, when they drain water out of a lock to lower a ship, they're going to save about 60% of that water in those basins and bring it back, so they will not need as much water as they would otherwise. Here are the locks coming in. The locks were made in Italy and brought by sea. They're about 4,000 tons each. And this is a very recent picture of the locks at the north end. Aqua Clara is what they're calling them. Here's one of the rolling gates. So it's kind of an overhead view. There's water here. This is a new lock here, but it's empty because it's still under construction. So it doesn't look like this moves, but this moves. It rolls right back into there. You can see there's water in there. And here's the backup, the other rolling gate over there. The scale of it is it's hard to tell, but so there's a little guy right there. The water-saving basin. So I didn't do this. The Panama Canal Authority did this. You can see water going into this one, and this one, and this one. That water you lose, it goes out. That ship goes away, and then you fill up the lock. Comes from basin 1, basin 2, basin 3. It's not new to the lock business. It's new to the Panama Canal. They're using these in Europe. This is a little computation that says what they're really saving is 60% of the water. So remember the amount of water that we used for the old locks was 52 million gallons of transit. It's only 45 million for much larger locks for the new one. So it's a very clever design. So what are they doing with this? Well, they raise the tolls. They've been raising the tolls every year or two for the last 10 years to pay for this. The new toll started April 1st. If we go through the Panama Canal, we will not use the new locks. They'll be saved for the largest ships. They'll be more expensive, and the pricing scheme is, I would say, very clever in that a ship will pay more to go through the new locks than the old, but a ship loaded will pay less per unit of cargo because it can carry more. so the ship operator can tell its customers it's cheaper to do this, and the Panama Canal can tell its board of directors, we're getting more money from these guys doing this. And the other thing they've done, which you will be very familiar with, is they have a frequent flyer program, which says, they call it the loyalty program, and what it says is, if you move a minimum amount of cargo through there in a year, then the price goes down. And if you move twice that, the price goes down again, and it keeps going down. The more business you do on the container side, the lower the price will be. So they're very clever, and they're very clever at dealing with their customers. That is, they're not keeping this a secret and posting a new price tomorrow, which maybe an airline or two might do, but they're sitting down with their customers and saying, look, we need the money, this is what we're going to do with it, here's how we're going to change the services, we're going to give you 6 months notice, and we want your comments on it. So they're very clever marketing guys. They have a few problems. The new locks leaked a little bit. Doesn't look like much, but when you zoom in on that picture, it's not like a leak in your shower. This is a lot of leaking. They got that under control. They've had a whole series of disputes and strikes. The estimated cost of this expansion program is $5.25 billion. My prediction is it'll probably be $8 billion when they're done, but they're in denial right now. So it's going to be they're ready for the next 100 years, and I'm ready to go with you again in February of 2017, and I'd love to answer questions if you have them. Yes.
Can you remind us again, what year did they finally deal with the mosquito problem? And as I understand it, the United States' major concern really was, as you pointed out actually, the health concern, because there were so many people who actually did die before.
Huge numbers. So when the French people came over, the managers, they brought coffins with them because they knew that the probability of dying was very high, and whole families were wiped out. First of all, I'm an engineer, so I am not obligated to know dates other than my anniversary, which is the combination on my suitcase. But about 1906. About 1906. So U.S. came in 2004, and it took them like a year to figure out that this is a problem, and less than a year to solve the problem. And again, it goes back to my view of engineering, which is, so tell me what the problem is, and now I'll figure out what to do. Yes?
Slightly off topic, what's the condition of the 100-year-old concrete?
Great. I mean, it doesn't look new, but it's in really good shape. So a lot of people have said, well, you know, we gave it back to the Panamanians in 1999, and they let it go to hell in a handbasket. It works great. It works really well. They have figured it out that they need this for their economy. Otherwise, they're nothing. Panama City is the financial capital of the Central America. You probably read about that in the newspapers recently. So yeah, it's really good, and they've done really well with it. And the construction of the new construction it's been absolutely global. So you look at who's doing it. It's all the big contractors from everywhere. You know, their accountant is Deloitte. You know, they buy top of the market. Yes.
Talk a little bit about security in today's world down there. Is it?
You don't feel it when you're there. No. You don't feel it when you're there, and people don't talk about it. But my sense is that the Americans aren't really very far away. So I think they're pretty secure. There certainly is a vulnerability. I mean, it wouldn't. You and I could sit down and figure a way to interrupt the operation of those locks. I mean, everything is fenced. Everything is, you know, razor wire and stuff like that. But you don't see a real significant presence of security people. So I don't know whether to worry about it or not. Yes.
When they were nationalized, did we get compensated in any way as far as the money?
No, but remember, we stole it in the first place. Yeah, because the guy that signed the agreement with the United States was a guy that didn't represent the nation of Panama. So no, but it was a gradual transition, and they got a lot of advice and support. But it was in really good shape to start with, and it's only got better. Yes.
Assume a worst case scenario, and there's with climate change, the rainforest disappears. After all, they're disappearing all over the world. Why can't you use seawater?
Well, remember, the water goes from top to bottom. It's driven by gravity. So you'd have to find a way to get the seawater up there. So you'd have to pump it. So that starts, and you need energy to pump it. And right now the source of energy is hydroelectric power. So it wouldn't be very easy to make that kind of change. It would be a lot more sensible to try to protect the rainforest, so that's what they're doing. They're increasing the storage capacity. And a lot of that, they lost some of that rainforest because it went to agriculture, and they're trying to turn that back around and restore the rainforest because they figured out that rainforest is really critical to them. But I wouldn't, it's not that it's inconceivable, but it would be, you'd have to make massive changes in the energy balance there in order to use seawater. In fact, what they're doing is exactly the opposite. What they're worried about is with a new set of locks, you'll have more saltwater intrusion into the fresh water. That's their drinking water supply, that lake. So they want to protect that, and they want to protect the ecology there. So they're working to try to reduce the saltwater intrusion.
Joe, time for 2 more questions.
Okay, 2 more questions. Hard one and an easy one. Hard one right here.
What do you do when a ship sinks or has problems?
I get off as fast as I can. You mean in the lock? Well, they've had accidents there, but remember, I won't flip back on the slides. But they have 2 parallel channels right now. They have 2 locks, one on each, right next to each other, with a common wall. So they'll take a lock out of service. They'll call that taking a lane out of service, and they have very heavy equipment there that gives them the capability to move something out fairly quickly. It's an interesting long story, but they've got a very huge crane there that they could use for that kind of stuff. That was German war reparations. That the Germans built it, and they came to the United States and went to Panama. So yeah, they pay attention to that, and they'll restore it very quickly. And now they'll have another channel, so they're even less vulnerable to that kind of thing. The rules and regulations are very strict about how the ship has to be equipped. They inspect the ships going through. So they figured out that they cannot afford to lose capacity for very long, so they're quite careful about that. But just go to the lifeboat drill on the ship. Be ready. Yeah.
Do you think that today, if this canal was in some way or another built on American ground, do you think with the regulatory environment that we live in today?
Couldn't have done it in 10 years, I can tell you that.
Well, that's what I'm saying. Could it even be done?
Well, I don't think I'm smart enough to know that. I mean, I would say the answer is yes, but the complexity would be very, very high. I mean, one of the issues, they are paying a lot of attention to environmental issues on the expansion program, or at least that's the great claim that they make. Yeah, the world is different, but I think it's different because it's a much more multidimensional world that we understand now than we understood before. So there were things done then that it would be unconscionable to do them then. We wasted 25,000 people there before we figured out what the problems were. So yeah, it would be harder. Everything is harder today, but what we hope is maybe some things are better. I don't know. Okay, am I out?
You're out. Ladies and gentlemen, thank you very much, Joe.
Okay.